So it was late at night, about 11 p.m., and I was working late, and I get this email saying that this event had been detected. And it seemed quite incredible. And so immediately called up all the telescopes that I had access to around the world to get them on this event. It was incredibly exciting because we've been waiting for this for years, and it seemed too soon and too close, but it was true, and it was an amazing event, and it didn't let us down. It produced light, all wavelengths of light, including optical and radio, so we were able to study it in unprecedented detail. We learned an enormous amount. We learned that these types of events create gamma ray bursts. They create an explosion called a kilonova, and we learned that gravity waves travel through the universe at the speed of light, something we can confirm, that where exotic elements like gold and platinum, where they're formed and how they're formed. It also let us have a way to measure the expansion of the universe, how fast it's expanding, and the age of the universe. It's quite an incredible discovery.
This is one of the biggest discoveries in physics in the 21st century. We detected the collision of two neutron stars, and these two neutron stars, they spiraled in on one another, and then they collided. This is the first ever time that we've observed a collision such as this, or anything in the universe, using both gravitational waves and light. These two neutron stars, they collided approximately 100 million light years away from Earth. And the gravitational waves, as well as the light, has been traveling towards our gravitational wave detector and also towards our telescopes for 100 million years before we finally detected it on the 17th of August of 2017.
This is really a landmark discovery for astrophysics. Even with just one event where we can see the explosion that accompanied these gravitational waves, that already confirms many predictions, such as how the heavy elements in the universe were created, what happens when neutron stars collide, and even how fast the universe is expanding. This is just the beginning. It's as though we've discovered a whole new sense. We can feel the universe now as well as seeing it, and I've no doubt the biggest discoveries are still to come.
To observe a gravitational wave at the same time as a gamma ray burst is an incredibly difficult observation to make because of the instruments that we're using to observe these and because of the rates that we expect these things to occur in the local universe. So to detect gravitational waves, if you imagine the distance between us and the nearest star, and then imagine the width of a hair, and detecting that width of a hair in that length, that's what we've got to do. And I can't believe we can do this, but we can. And we've got to go even deeper and even more precision to detect the inner workings of supernova and primordial backgrounds. So there's a lot to do and a lot to look forward to.
The LIGO-Virgo collaboration has recently announced the detection of a gravitational wave signal from the merger of a binary neutron star system. What's special about this is that when neutron stars collide, they emit not just gravitational waves, but also electromagnetic radiation like gamma rays, light, and radio waves. And the Fermi gamma ray satellite was also able to see a pulse of gamma rays come from the same event, and the optical telescopes have been monitoring a flash decay in the optical light coming from that event as well. And so this is really the first time ever that we've seen both something we know something about, so a binary neutron star system, and we're able to say exactly where it is and correlate it with conventional optical astronomy and gamma ray astronomy. So this is really the birth of multi-messenger astronomy. It's the first example, and we hope there will be many more examples to come.